October 8th, which is a Friday. And by the way, for those of you on Zoom, the test will require it to be proctored. So you can either attend in class or you can arrange it with the testing center or something like that. Okay. Any questions about the test? The format of the test will be, there'll be a few multiple choice questions. And then there will either be 6 to 8 short problems, or it may be that there's 4 short problems and 1 problem that's kind of long and has parts to it. But I will tend to lead you through the, in part A do this, and part B do this, and so on. So that would be the format of the test. Any questions on that? Okay. All right, so today we are going to put to use the set of equations that we developed in the last class for the special case of motion with constant acceleration. Yeah. Oh. And so whenever you have an object moving with constant acceleration, then these 3 kinematic equations are always true. So the first one gives you a relationship between velocity and time. The second one gives you a relationship between position and time. And then the last equation we get by combining the previous 2 equations. We just eliminate the time variable from the previous 2 equations. And that gives us this other third equation, which gives you a relationship between x and v in this particular way. So in some sense, all of the information really is contained in these first 2 equations. This third equation is simply a consequence of the first 2 equations. But we write it down because it can be very useful. Depending on the type of information that's given to you, you can maybe readily use this third equation right away. So we just kind of calculate it. Any questions on that? So today we're going to look at some examples where we put some of this to use. Again, here's a summary. So let's look at this particular example. We are told that there is an object moving with uniform acceleration. Again, uniform is another word for constant. Uniform acceleration, constant acceleration. Has a velocity of 11 centimeters per second in the positive x direction when its x coordinate is 2.73 centimeters. Again, a lot of words, but we will, once we draw a picture, it'll be a lot clearer. If its x coordinate 2.05 seconds later is minus 5 centimeters, what is its acceleration? That is the question. So the first thing that you want to do is parse all of these words into something that is understandable, that you can relate to equations and pictures. So let's go ahead and first draw a picture. So this is an object moving along the positive x direction. So let me just go ahead and draw an axis. So let's say that that is your positive x direction. And then it's giving you some coordinates. It's saying that when its x is 2.73 centimeters or something like that. So let's go ahead and define an origin. This would be like your x equaling to 0. And then it says that it has a velocity of 11 centimeters per second when it is located at 2.73 centimeters. So 2.73 centimeters is going to be somewhere over here. So let me go ahead and mark this as x equals 2.73 centimeters. And let me go ahead and draw a little picture for this object. So there's the object, whatever that is. It's located at 2.73 centimeters. And when it is at that location, we are told that it has a velocity in the positive x direction of 11 centimeters per second. Any questions on that? Then it tells us that a little bit later, its x coordinate 2.05 seconds later is it is located at -5 centimeters. So where's -5 centimeters? It's going to be to the left of x equaling 0. So that may be somewhere over here. That's your x equals -5 centimeters. And so a little bit later, the object is over here. Any questions on that? Now, the strategy here is that we're supposed to take this information and we're supposed to find what is the acceleration in this question. So what we want to do is we want to translate this word problem into what it means for us in terms of our master equations. So our master equations are v equals v naught plus at, x equals x naught plus v naught t plus 1/2 at squared, and v squared equals v naught squared plus 2a x minus x naught. Right, those are the equations that we will look at. The truth lies somewhere in these equations, and we need to extract it. And you should just have these equations in your head, bust them out at parties and stuff, at least for the semester. So let's do a little dictionary here. We're told that the object is initially here, and then a little bit later it is over here, which means that this moment here is our t equaling 0 right there. And over here is our t equaling 2.05 seconds. Right? So what does this 11 centimeters per second? There's a question here. Oh. Yes, the code is 0335. So what that means is that at t equaling 0, all the information given to us here corresponds to the initial velocity, the initial position, and everything over here corresponds to the final position and whatever, all the final stuff. So if I were to look at this problem, I will immediately realize that I can write down that this is actually v naught. This is the initial velocity at time t equaling 0. Does that make sense? Also, this is x naught. Or maybe I'll do it in the following way. This is equal to x naught. Right? That is your initial coordinate at time t equaling 0. This here is equal to your x. Well, it's just x. I hope that's not confusing. You guys know my wife, right? And so if I collect that, what do I get? I get that x naught here is 2.73 centimeters. I get that my final x is -5 centimeters. V naught is equal to 11 centimeters per second, and t is equal to 2.05 seconds. This is the information that is given to you. And the thing we are supposed to find is the acceleration, which in these equations corresponds to a. So the thing we're supposed to find is a. So what I have done is I have translated the word problem into a picture and into quantities that I can now work with. The bottom one?
Yeah.
Oh. How do I deal with this?
Is it because the name's at the top?
Oh yeah, maybe I should put them on the side. Any questions so far? And so next, all we're going to do is look at those equations on the right and see if there's something that helps us find the acceleration. First off, is anyone confused by what's happening in this problem? They're telling you that the object is moving to the right, and then a little bit later, it's on the left. Anybody confused by that? Does anyone see what's going on? How is that physically possible? Well, this is a problem where you can already figure out that the acceleration of this object is going to be negative. Because what's going to happen is the object is it's going to the right, it's going to be slowing down, it's going to come to a stop, and then it's going to move backwards in this way, all of it at constant acceleration. So its velocity will change, but its acceleration will be constant. So an analogy I can think of that might describe the situation is perhaps you're going in a sailboat and you're moving in the positive x direction, but there's a wind in the opposite direction, and that's causing the sailboat to slow down. It'll come to a stop, and then the wind will keep pushing it, and then it will start to go back the other way. And we will see later on, accelerations are caused by forces. So you can imagine that there's a constant force from the wind, and so it comes to a stop and then starts to go back in the opposite direction. Yeah.
So you said that it's coming back in the negative direction and then it starts going back in the positive direction?
The other way. So this is the positive direction here. Sorry, did my pen just die? Oh, am I logged out of Zoom here? No. Huh, I can't seem to use the pointer. Okay. So this is the positive x direction. So initially, the object is moving to the right in this way. It's going to come to a stop, and then it's going to turn around, go backwards, and then it's going to travel in the negative x direction and come all the way here. That makes sense? Why is this not working? It's going to give me OCD for the rest of the class. No. All right. Okay, so now let's take this information and look at how we can solve for the acceleration. So the first thing I can do is, oh, there it is, thank God. That was going to drive me insane. Class. Okay. So here is the first equation. Can we solve for the acceleration using this equation? Take a moment, think about it, and yell out an answer if you think it is possible for me to use this equation, the very first one, v equals v naught plus at, to solve for a. Say that again? Exactly. So that's correct. We can't use this first equation directly because in order for me to solve for a, I need to know all these other three variables. I do know that t is 2.05 seconds. I do know that v naught is 11 centimeters per second, but I do not know what v is. They have not told us what is the velocity of the sailboat at this location. So because I don't know what this v is, I can't use this equation directly to figure out what is my acceleration. Okay, so then let's go back to the second equation. What about this one? Can we use this information? Um, Anyone, can we use the second equation here to solve for A? Yes, it looks like we have everything that we need. We know the time, 2.05 seconds. We know V naught is 11 centimeters per second. Again, the time here is known. X naught is 2.73 centimeters, and X is minus 5 centimeters, and so on. So in some sense, we're done. We could use the second equation. The third equation is also something we cannot use because, again, we don't know what V is. We know everything else, but we don't know what this V is, so I can't solve for A. And that's basically the strategy. And as you get some practice with it, you will start to be quicker at identifying what needs to be done. So we will say here that let's go ahead and use X equals X naught plus V naught T plus 1/2 AT squared. And then I will solve for the acceleration. And doing a little bit of algebra here, let me bring everything to the left side. I'll have here X minus X naught minus V naught T is equal to 1/2 AT squared. And then I'm going to isolate A by multiplying both sides by 2 and dividing both sides by T squared. And so therefore you will get here that A is equal to 2 times X minus X naught minus V naught T divided by T squared. Any questions on that? Again, I strongly encourage you to work with symbols until the very end. If you just start plugging in numbers, after a while, you get lost in all the numbers and you don't know what's going on. So now that you have this, you can now go ahead and plug in numbers. This is 2 times minus 5 centimeters minus 2.73 centimeters minus 11 centimeters per second times 2.05 seconds. Let me make this a square bracket here. And then we are dividing all of that by 2.05 seconds, the whole thing squared. And if you work this out, notice the units here, it's centimeters, centimeters. The seconds here cancel. So this will also be in centimeters. And then you have something here in seconds squared. So the overall units will be centimeters per second squared, which are indeed the units of acceleration, centimeters per second squared. And let me just go ahead and look ahead and see what the answer here is. This came out to be minus 14.4 centimeters per second squared. And then we will go ahead and box the final answer. Another request I would make is box your final answer in the final exams. I think there's like 60 of you. It's a lot of grading for me to do. So I would appreciate if you it'll put me in a better mood, which is good for your prospects. But yeah, and I do give lots of partial credit. So the more work you show, the more symbolic equations you show, even if you don't get the right answer, that's fine. You will get most of the credit because, again, I don't care that it's minus 14.4. The number is the least interesting thing to me. It's more important that I see that you're able to figure out what the answer is. So the stuff that comes before the final answer is way more important. Any questions on that? Okay. Okay, so next we are going to talk about freely falling objects. So here, remember my juggling, right? You throw a ball up in the air, falls back down. Amazingly, gravity is an example where objects under the influence of gravity near the surface of the Earth are actually moving at constant acceleration. So we are going to study freely falling objects. This is Galileo. You guys may have heard, I don't know if it's true or not, but apparently he was dropping objects from the Leaning Tower of Pisa to study the motion of freely falling objects. They had a lot of time back then. They didn't have distractions of YouTube and stuff, so you could ponder the nature of things. This is he was a pretty amazing guy. He made incredible contributions to physics in the study of kinematics, dynamics, astronomy. He I think he discovered some moons of Jupiter. One of the advocates of heliocentrism, that is, the sun is at the center of the solar system, not the Earth. And what was amazing about him is that he was, we don't have this anymore today as much. He really was like a Renaissance man. Today we are all trained to do some very specific narrow things, and we don't know much about everything else because everything is very specialized. But he was looking and doing astronomy and looking at objects in the sky, and he couldn't see them very well. So he took a break and went and invented a better telescope. So they didn't have Amazon back then that you could just order parts, so that you had to really build things from scratch. So it turns out that if you measure the acceleration of objects that you drop in free fall, then you will find that all objects, amazingly, fall at exactly the same acceleration of 9.8 meters per second squared. It's kind of a remarkable thing. It doesn't matter whether you're dropping a bowling ball or a feather. If you take out wind resistance and that kind of stuff, everything will fall at exactly 9.8 meters per second squared. And so that therefore tells us that we can, in fact, even if we don't know the cause of gravity, we haven't yet studied a theory of gravity, we just take this experimental observation that everything seems to fall at a constant acceleration of 9.8 meters per second squared, then all this stuff that we developed, these kinematic equations for a constant acceleration, can be directly applied to objects in free fall. Any questions on that? We will introduce the symbol G, which is defined to be a symbol for this numerical value of 9.8 meters per second squared. So depending on which way you define your positive direction, so an object is falling down, for instance, if you define the positive direction upwards, then it will have an acceleration of minus g, because it will be a negative acceleration. If you define the positive direction downwards, then the acceleration will be plus g, or plus 9.8 meters per second squared. So g just denotes the magnitude of gravitational acceleration. Yeah, so that's kind of what I say here. The acceleration will either be of freely falling objects will either be plus g or minus g, depending on which way you define your positive y direction. In fact, let me show you guys a video on YouTube. Have you guys seen the video of astronauts dropping objects on the surface of the moon? Not most of you, okay. So let me do moon. So in, I guess, 1969 or the early 70s, in one of those missions, on the surface of the moon, you could really test out this idea of uniform acceleration, of constant acceleration for all freely falling objects, because there's no atmosphere on the moon. So there's no wind resistance, or there's no effects like that. So on Earth, when you drop a feather, it kind of does this. And that's because of the aerodynamics and the air resistance that it's facing. But there's none of that on the moon. So on the moon, if you drop a hammer and a feather together, they should fall at exactly the same rate. And so they actually tried that. They used Newton's equations to get to the moon, and then they tried to verify that this thing works. And so here it is. Okay, let's cross our fingers and hope that everything works here. I'm going to turn up the volume on the laptop.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Which proves that Mr. Galileo was correct in his findings.
Yeah. Any questions on that? I noticed that they didn't seem to fall as quickly as they would on Earth, and that's because on the moon, the moon is a smaller planet, so the force of gravity there is weaker. So there, the acceleration is not 9.8. I forget what it is. I think it's something like 1.6 meters per second squared or something like that. So all objects there fall with that uniform acceleration. And by the way, just as a foreshadowing, an amazing thing that we will do in this class is we will actually derive from a theory of gravity this number, where this number 9.8 comes from. We will actually derive it from first principles. It will depend on the mass of the Earth, the radius of the Earth, and the gravitational constant G. We'll have an explicit formula for where this comes from. So here is my kind of statement about when does the object, a freely falling object, have positive acceleration versus negative acceleration. So here, if I define my positive y direction to be downwards, what does that mean? It means that when I set up my coordinate system here, the tick marks are increasing downwards. 0, 1, 2, 3, 4, 5, and so on. So if an object is now falling freely, its acceleration will be pointing downwards in the positive y direction. And by the way, notice that the acceleration due to gravity is always pointing down towards the surface of the Earth. So even when the object is traveling up, because its acceleration is down, the velocity and acceleration are equal, are in the opposite directions, and that's why it's slowing down. On its journey down, its velocity is down, the acceleration is also pointing down, they're pointing the same direction, and that's why its speed starts to increase as it's falling down. But the acceleration, the direction of the acceleration is always towards the surface of the Earth. And in this case, it would be positive because you've chosen your positive direction to be downward. If you chose your positive y direction to be upward, then the acceleration due to gravity will be minus 9.8 meters per second squared. Because the direction of the acceleration is downward, the positive direction is upward, so you're pointing in the negative y direction. Any questions on that? So for freely falling objects, we would basically have our same equations, but we would have like v equals v naught plus at, and then instead of x, we could say, in case you have OCD about using x for the vertical motion, you can replace it with y, and you will say y is equal to y naught plus v naught t plus 1/2 at squared, and then you will have v squared is equal to v naught squared plus 2a y minus y naught, and then your a here will either be plus g or A will be minus G, depending on which is the positive y direction. Any questions on that? Okay. So let's do an example problem here. So in this problem, what are we told? A ball is thrown up from the top of a building. So they launches the object upwards with an initial velocity of 20 meters per second straight upwards. So already they're giving us some information here. They tell us, first off, the positive y direction is upwards, just because of the way they have labeled their coordinate system, right? This is y naught is equal to 0 here, and then they're calling this y 20.4. That means the tick marks are increasing upwards. So in this case, is the acceleration due to gravity positive or negative? Anyone? The positive direction is upwards. How many people say it's positive? How many people say it's negative? See a few hands. How many people don't know? If I'm saying the positive y direction is upwards, then is the acceleration of this object plus 9.8 meters per second squared or minus 9.8 meters per second squared? Is it positive or negative? Minus.
Minus.
Yep. Someone from Zoom also says minus, and minus is in fact the correct answer. Because the acceleration due to gravity is always pointing downwards. And so in this case, your A will be minus G because the downwards is in the negative y direction since you've defined the positive y direction to be upwards. So anyway, so also notice that they have set up their coordinate system in such a way that they're saying that at this location here, this is what they're calling their y equaling 0. All right, so they have labeled this as y naught equaling 0 there. So that's the launch point is y equaling 0. What will be here's another question just before we get into the problem here. What is the y coordinate of the floor down here? If I tell you that this is y equaling 0 and the positive y direction is upwards, what will be the y coordinate of the floor? Based on this picture, negative 50 meters, right? So this distance is 50, but you're taking 50 units in the negative y direction. So down here will be minus 50. Okay, so the first question is, determine the time needed for the ball to reach maximum height. So this person launches the object, goes up, it comes to a stop, and then falls back down. So this is the maximum height, and they're asking us to figure out what is the time needed for this object to reach maximum height. So let's go ahead and do that. So let's look at part A. We need to find the time needed to reach maximum height. And what does that mean? We are analyzing, in this case, this part of the journey right here. Whoops. We're analyzing this upward part of the journey. Right, that's our, so what does that mean? It means that this is our y maximum height. This is our initial height. So this is our t equaling 0. So all the initial stuff is happening here. All the final stuff will happen here. So once again, let me go ahead and write down all of our master equations. I'm going to say here v equals v naught plus at, y equals y naught plus v naught t. And in this case, our a is minus g. So I can actually go ahead here and say minus 1/2 gt squared, because I'm using the fact that a is equal to minus g. So in fact, I could actually go up here as well and make this minus gt. And v squared is going to equal v naught squared minus 2g y minus y naught. Those are the master equations that we are using here. Any questions on that? Let me actually go ahead and also write explicitly this is equal to minus 9.80 meters per second squared. So let's collect some information. We are told that y naught is 0. And then y is what we need. Y is not given to us at the moment. We're not given y. We are told that the initial velocity is 20 meters per second. So that means v naught is 20 meters per second. We know that the acceleration is equal to minus g, which is minus 9.80 meters per second squared. And what else are we told? I think that's about it. And then the question is, what is the time needed to find for it to reach this maximum height? Now there's one more piece of information. See if you can figure out what that is. What happens at maximum height? There's one more piece of information that we could use in these equations. I can.
The velocity is 0.
Thank you, exactly. As the velocity is 0, right? So the object goes up, comes to a stop, and then falls back down. So in fact, we know this case that the other piece of information we have is that actually v is equal to 0. The final velocity is 0 in this term. Any questions on that? So again, this is sort of like they're giving you some code, right? They're telling you maximum height. Immediately that in your head should register, oh, at maximum height, it has 0 velocity, v is equal to 0. They will not explicitly tell you that it comes to a stop. So what can we do to find our time? Can we use the first equation? Yes, we can. We hit the jackpot right away. So we can go ahead and use v equals v naught minus gt. And so therefore, I need to solve for time. So that is equal to, or let me say, therefore, gt will equal v naught minus v. And therefore, t is equal to v naught minus v over g. And so that is the same as, what is v naught? It is 20 meters per second minus 0 over 9.8 meters per second squared. Notice the meters cancel, then you have 1 over seconds, and then you have seconds squared in the numerator, so you will have units of seconds. And so therefore you end up with 20 divided by 9.8 seconds. And what does that equal to? Let me look ahead. That's about 2.04 seconds. So therefore your t is equal to 2.04 seconds. So we have figured out how long it takes the object to reach its maximum height. Any questions on that? All right, I think we have just 2 minutes left, so maybe this is a good stopping point. So I'll go ahead and stop here. So again, just a reminder, your test will be 3 Fridays from now, October 8th. And I'll post another problem set tonight. And we will do more of this on Monday, and then you should be set to do that problem set.